For this next lesson, we're doing exponential growth and decay, which is built off of exponential form, which is why I have this formula here. And I'm also going to show you a different way that this formula can look. Another way that this formula can look is y equals, let's see, we have the starting number times, this one would be 1 plus or minus the growth rate or decay rate, and then that 1 plus the growth rate or 1 minus the decay rate will be raised to the power of time normally. In this first example, write the equation of the population t years after 2000. We have it increased from this, so it started here, it ended here, and it changed 5 years. It gave us the growth rate, 4%. So we're going to start with y equals the starting amount times 1 plus the growth rate, 0.4%. So then that as a decimal, because this number 1 is a decimal, it's not a percent, that number 1 right there, we're going to need to change that percent into decimal. So 0.4% is equal to 0.004 as a decimal, and then we're raising that to a power, and it says t years after 2000. So we'll put power of t, because each of those t years is measuring after 2000. Use the equation to predict the population in 2015. So now we're just going to copy that down. Times 1.004. Add those two numbers together is what I did. And then 2015 is 15 years after 2000, so power of 15. You'll need to use a calculator. You can use Desmos. I'm going to use my graphing calculator. 8502464. So that means it increased about from 8,000 here to 502,000. It increased by 494,000 people in those 15 years. In the second question, we have this green food company, and they're going to make savings plans. Here's the starting amount. Here's the rate of interest, and here it says interest is compounded quarterly. Whenever they give you the interest rate, the common way to do it is the rate for the year. They call that the APR, the annual percentage rate. But here it says that we're going to compound this interest quarterly. So quarterly means every 1/4 of a year. If this is the interest for the entire year, but we're going to compound, we're going to use the interest formula every quarter. Every quarter means every 1/4 of a year, we're going to use the formula. So that means we're going to have to make some modifications of the formula, because this formula from the top, this is for time periods of 1 year. So if we're going to be doing it every 1/4 of a year, then the formula we're going to use is going the starting amount times 1 plus the growth rate. The growth rate was 8%, which is a decimal is 0.08. And then since this is the growth rate for the entire year, but we're going to use this formula quarterly, which means every 3 months. So if we're doing this every quarter, then we are not using the entire interest rate whenever we're doing this. We have to scale the interest rate down to be the quarterly interest rate, which would be 1/4 of the yearly interest rate. Then what we also do for the formula in this question is if we're compounding it quarterly, and then they gave me the scale here of years, they said 5 years, my exponent is not just going to be that 5 years. The exponent can't be those 5 years because those 5 years, in each one of them, it got compounded 4 times. So we have to put 5 times 4. So now we're going to use the formula, or we're going to simplify this to be 1,000 times 1/4 of 0.08 is 0.02. So 1.02 to the power of 20, which is 1,485.95 . In the next part, they want to keep the money in there for 35 years. Okay, so then we're still starting with $1,000. And the formula says 1 plus the growth rate. The growth rate is 0.08. We're compounding it quarterly, so we're going to divide by 4 because there's 4 quarters in a year. And then, because we're doing 35 years, we're going to take that 35, we're going to multiply by the number of times it compounds. The number of times it compounds is 4 times in a year. And then we can simplify this. And this answer is $15,996.47. So that's not a ridiculous amount of money, but for this guy who just has, or for this company who's putting only $1,000, $1,000 isn't really a lot of money to put into a savings account. Normally you would put like $1,000 every year if you really want to have tons of money. But even though they only put $1,000 after waiting 35 years, so they get it like at the start of the job, by the time they're retiring, they have almost 16 times their starting amount just by letting the money sit. And then we can do one last example. Here, starting 15% depreciation, so that means we're going to lose, this is decay, decay 15% each year. How much will they pay for the car? So they're going to buy this car, they're going to sell the car, and then how much is in between those two amounts is, the mom bought the car and they're going to sell it to the daughter. So the daughter's going to pay it for it. So they just want to know how much is this car worth after 5 years. So that would just be y equals 9,000 times 1 minus 0.15 to the power of, we're talking about 5 years later, 5. 9,000 times 0.85 to the 5th power. $3,993.35. That's how much the daughter's going to pay, which is a lot. I think a mom should give their daughter a better deal. It's a 5-year-old car. It only cost them $9,000. It should be like $2,000.